Assalamu alaikum. I am Saji Afrin from the Department of Computer Science and Engineering, Daffodil International University. It is my pleasure to present our research titled Graph Theoretic and GNN-Based Framework for Surplus Demand Matching in Rooftop Farming Networks. So here is our presentation outline. First of all, abstract. Rapid urbanization is reducing agricultural land, particularly in densely populated cities like Dhaka. Rooftop farming has emerged as a sustainable solution to improve food security and environmental resilience. However, one major challenge persists. Surplus produce is frequently wasted due to inefficient surplus demand matching mechanisms. Traditional matching methods struggle because rooftop networks are sparse, geographically sensitive, temporally dynamic. To address these issues, we propose a hybrid, scalable, proximity-aware framework that combines maximum weight bipartite matching and graph neural networks including GCN, GAT, and GraphStage. This hybrid approach improves scalability, flexibility, and real-world feasibility. Urban food demand is steadily increasing. Rooftop farming is expanding across cities like Dhaka as households attempt to enhance sustainability and local food production. Despite this growth, several problems remain. First, surplus produce is often wasted. Second, consumers cannot reliably identify nearby suppliers. Third, there is no intelligent automated matching mechanism. Most existing systems are either manual or lack optimization and learning capabilities. This results in efficiency, food waste, and increased carbon emissions due to unnecessary transportation. Our study aimed to model surplus demand interaction using graph theory, integrate classical optimization with GNN-based learning, reduce food waste and transportation distance, support scalable smart city food distribution system. Literature review. Research in rooftop agriculture primarily focuses on sustainability and food security but lack automated matching frameworks. Classical matching methods such as bipartite matching and linear optimization provide interpretable solutions but struggle in dynamic large-scale environment. Graph neural networks have shown strong performance in relational data modeling. GCN captures structural information, GAT introduces attention-based age weighting, GraphStage enables inductive learning for unseen nodes. However, no prior research integrates MWBM with GNNs, especially for farming networks. This motivates our hybrid approach. Methodology. Our framework consists of 5 major stages. First, data ingestions of rooftop surplus and demand nodes, spatial and temporal preprocessing, baseline optimization using MWBM, GNN-based link prediction, post-filtering, and evaluation. This pipeline ensures both interpretability and scalability.
Data collection and preprocessing. For this study, we collected rooftop farming data from Dhaka. The dataset includes features such as user ID, location, whether the entry represents surplus or demand, quantity, category of produce, and exchange type. Before applying any model, we performed pre-processing steps including encoding categorical variables, scaling numerical features, calculating geographical distances, and defining availability windows. We also applied geospatial mapping to better understand spatial distribution pattern across the city. This prepared dataset served as the foundation of our graph modeling and matching framework. Geographical analysis. Next, we analyzed the geographical distribution of rooftop nodes using map visualization with pop-up details. We identified clusterings, patterns, and distance relationships between surplus and demand points. These geographical insights were directly integrated into our matching process. Especially, we assigned higher edge weights to geographically closer pair, ensuring that local exchanges were prioritized.
We first conduct a bipartite graph where one partition represents surplus node, the other represents demand nodes. Edges are created when items match and exchange types align, availability periods overlap. Edge weights are defined as the inverse of geographical distance, prioritizing nearby matches. We then apply maximum weight bipartite matching to produce optimal one-to-one matches. But there are some limitations. Strict one-to-one constraints. Many nodes remain unmatched. Limited flexibility. Poor scalability in dynamic networks. So these limitations motivate the learning-based extensions. Second is GNN reformulation. To overcome MWBM limitations, we reformulate matching as a link prediction problem. Instead of enforcing rigid pairing, we estimate the probability that a surplus node should connect to a demand node. Process. Nodes are converted into embeddings. GNN encoder, GCN, GAT, and graph stage are applied. A matchability score is computed as the dot product of surplus and demand embeddings. Matchability score is equal to embedding multiplied by embedding surplus multiplied by embedding demand. Training setup. So positive samples are from MWBM matches, negative samples are from random unmatched pairs, loss function, binary cross entropy, and optimizer Adam. So finally we apply a 5 km post filter to ensure environmental feasibility and reduce carbon footprint. The hybrid approach combines the strength of both methods. MWBM provides an interpretable optimal baseline, GNN captures hidden relational patterns, GraphSage supports inductive learning for new rooftop nodes. The system becomes scalable and adaptive. This makes the framework practical for real-world urban deployment. Result and discussion. So MWBM baseline result matching is 44.96%, average distance 5.03 km, quantity matches ratio 80.3%, availability gap 1.8 days. Although interpretable, MWBM suffers from scalability and constraints. GNN performs comparison among the tested models, so GCN and GAT demonstrated moderate performance but were less stable. And GraphSage performed best in sparse urban network due to the inductive capability, making it suitable for expanding rooftop ecosystem.
After training the GNN models, we generated predicted matches between surplus and demand nodes. However, to ensure practical feasibility, we applied a distance-based post filter. Only matches within 5 kilometers were trained. While GNNs provide flexibility in predicting potential links, this post filter grounds the recommendation in real-world logistics. As a result, transportation costs are reduced, food spoilage is minimized, and exchanges become more practical within the dense urban environment.
In conclusion, we proposed a hybrid graph theoretic and GNN-based framework for surplus-driven matching in rooftop farming networks. Our system improves surplus utilization, reduces transportation distance, minimize food waste, support smart city integration. GraphSage demonstrated superior generalization and scalability. Our future works include real-time dynamic graph updates, integration of weather and seasonal data, multi-objective optimization, deployment across multiple cities. So here are some references that we used for this paper. And finally, I would like to thank everyone for your attention.